So on page 17 in your notes, there's a past AP question that we're going to do before we do the next section. We are asked to find the derivative of f of ln x. And in order to do that, what we first need to do is figure out, well, what is f of ln x? So ln x is going in as the input into the f function. So I'll do ln x squared plus 2 times ln x. I've got a delay on my smartboard for some reason. That's going to get really old. Anyway, my derivative with respect to x would then be, first of all, I'd use the chain rule. I would do 2 times the natural log of x to the first times the derivative of the natural log function, which is 1 over x, plus 2 times the derivative of the natural log function, which is 1 over x. And then I have a common denominator, so it looks like I'm just going to have 2 ln x plus 2 over x for option A. That one did not have very good results nationwide. 60% of all students got that one wrong. So moving right along in the notes, we have been working on our derivative of the natural log function, and it stands to reason that if the derivative of the natural log function is 1 over x, then when I integrate 1 over x, I should get ln x because they're inverse functions, and that's exactly what we get. We have the absolute value here because negatives are outside of the domain for the natural log function. Recall our natural log function looks like this, and negatives cannot go into that function. Also keep in mind that when we're doing the integral of 1 over a function of x, we have to make sure that this is du, not dx. So we've got to be a little careful with our u substitution. So let's begin. Number 1 is a nice easy one. I like to always pull constants out front, so I'd have 4 times the integral of 1 over x dx, which is just going to be 4 times the natural log of the absolute value of x plus our good friend Carl the constant. And I'm done. Number 2, this would be my u, but that would be 1 over u dx. I need 1 over u du in order to use my natural log. So if u is 5x minus 2, then du is 5 dx. So consequently, dx is actually a fifth of du with that fraction correction in there. So when I rewrite this, I've got 1 over u 1/5 du. So I'm going to rewrite that with the 1/5 out front times the integral of 1 over u du. So that fraction correction that we've been doing with u substitution is still holding with our natural log functions. This is going to give me 1/5 of the natural log of the absolute value of u, where u is 5x minus 2, plus Carl. And I think we're just going to move right along over here to number 4. Let's pull the 7 out front because it's a constant. You don't have to, but I always think it just keeps things nice and orderly. The derivative of the bottom, which is always where our eyes are going to go now, we're going to go to the bottom and take its derivative and hope that its derivative is living on the top so that we've got this u prime over u or 1 over u du situation going on, because when we integrate that, we get natural log. And when I take the derivative of the bottom of this one, I get 2x dx, which is almost the rest of the integrand, or almost the top of the fraction. If I had 1/2 of it, I'd be rock solid, so I'm going to take a half. So now what I have is the 7 and I would have, what do I have here? This is, sorry, du is 2x dx. I forgot to write u equals x squared minus 4. I skipped a step. So I have the 7 that was out front. I have the 1/2 coming out front. And then I have 1 over u du. That gives me 7/2 natural log of the absolute value of u plus Carl. Now I'm going to take a minute to check this one because the checking is always good if you have time. And remember, if we've taken an integral correctly or an antiderivative, then when I do the derivative of my antiderivative, I should get the integrand back. Well, if I take the derivative of this function with respect to x, the 7/2 comes out front, and I really end up with the derivative with respect to x of x squared minus 4. And what that gives me is, oops, sorry, I forgot the natural log. It gives me 1 over u times du. And you'll notice what happens with this is the 2's cancel, and I get 7x over x squared minus 4. I get that original integrand right back. So I know I've taken my integral correctly. So now we're just going to go do a little practice, and it says usually think of u substitution with u being the denominator that's generating the numerator when you take its derivative, and in theory then we'll have a natural log, but that doesn't always happen, and so I've mixed on here ones where you do end up getting 1 over u du and ones where you don't. So on this one, I'm going to let u be 16 minus x squared, and you know what? I think I took the ones I wanted to do and I gave you more space on the next pages of your notes. Yep, I did. I remember doing that. So let's begin number 5, and again we're going to just go for our natural choice of u. When you take your choice of u and take its derivative, you're hoping to get the rest of the integrand or a multiple of the rest of the integrand. And on here I have negative 1/2 of du is the rest of the integrand. So when I write this out, actually I get negative 1/2 the integral 1 over root u du. This is not the natural log integral. This is actually an old one that I could have put on chapter 4 test. This is power rule where it's u to the negative 1/2 that I'm integrating. And remember to do that, I add 1 disguised as 2 over 2 and then divide by that exponent, which would end up being multiplying by the reciprocal. And what I end up with here is a negative u to the 1/2. My smartboard stopped on me, plus Carl. I'm waiting for it to catch up, so hopefully it will. So and then when I back substitute that in there, what I'm going to have is negative u to the 1/2, or equivalently, I don't know why my smartboard stopped writing. Come on. I'm hoping it'll come back to me here in just a second. I'm going to go click on the pen tool and see if, or maybe if I lift it up and start writing again. No! Just a second, I'm not ready to forfeit this set of notes. So oh, there we go. All right. So next up, what I end up getting is negative the square root of u. U was 16 minus x squared plus c. This did not have any natural log in it. One of the biggest mistakes they say kids make on the AP exam is what they call universal application of the natural log rule. You don't use it every time you see a fraction. You use it only when u is your denominator and you take its derivative and it lives on the top, or equivalently, thinking of u prime as du dx, you end up with this. So we've got to be really careful with that one. On this one, if I would let u equal x, the derivative is 1. It's got nothing to do with ln x to the 4, so poor choice of u. We usually go to the bottom and let u be the bottom, but not always. On this one, my u would be natural log, because when I take its derivative with respect to x, du dx is 1 over x. So du is 1 over x dx. I've got another power rule problem here. I've actually got u to the 4th du, which is u to the 5th over 5 plus our good friend Carl, and then substituting back in, it's just ln x to the 5th over 5 plus c. Now again, see the power of checking this. If I were to take the derivative of this, I'd bring the 5 out front, it'd cancel with the 5 on the bottom, knock it down to a 4, and then when I multiply by the derivative of the guts, I'd get ln x to the 4th times 1 over x, or equivalently, ln x to the 4th over x. So the checking holds on that one. Number 8, this is not a natural log issue because when I take the derivative of the bottom, I get 1. I do not get the top of the function. This is a if it makes a heart, break it apart problem. This is actually the integral of x minus 2 plus 1 over x. When I divide each term by the monomial on the bottom, I get 3 separate pieces in a sum and difference that I can integrate separately. The antiderivative of x is x squared over 2. Of 2, it's 2x. And the antiderivative of 1 over x, we've now learned, is natural log absolute value plus c. And I'm done. All right, so number 9, if I were to ask you what's the derivative of the sine function, you'd say cosine. If I were to say what's the derivative of the cosine function, hopefully you'd say negative sine. If I were to say what's the derivative of tangent, maybe you'd say secant squared. But if I were to say what's the integral of cosine, you'd say sine. What's the integral of sine x? Negative cosine. What's the integral of tangent? Keep in mind I'm asking you the derivative of what gives you tangent. We don't know that right now. I've never given you that because this is actually a natural log issue. Here's why. You might say, LaRute, it's not a fraction, and I'd say, yes, it is. Tangent is sine x over cosine x. And when I go to the bottom of the function and I consider that my u, then my derivative is the top of the function. It's a multiple of it, but that's all I need. So if I have negative du is actually sine x dx. So really what I've got going here is I've got the integral of negative u prime, or negative du, over u. Keep in mind that that is now ln absolute value of u plus Carl. So I now have a way to integrate not only tangent, but I could have done cotangent similarly. Next one, I'm going to let u be the denominator. I'm hoping that when I take its derivative with respect to x, I get the numerator or a multiple of it, and I do. So what I have right here is du, if you want to think of a 1 right there, and on the bottom I have u. So I have 1 over u du, which unfolds into a nice natural log absolute value of u. And again, I think the beauty of this is in the checking of it. Watch when I check it. To check it, I take the derivative of this function. The derivative of natural log of u is 1 over u times the derivative of u. And then Carl goes to 0, so I get that integrand right back at me. So they're nice to check. Let's go discuss number 12. Suppose I'd say, well, I'm going to let u be cosine. Well, the derivative of cosine is sine. It's not 1 over tangent. Well, then my other option is, well, I'll let u be tangent. The derivative of tangent is secant squared. And if you look at the rest of the integrand, it doesn't look like it's secant squared, but by definition, secant squared is 1 over cosine squared. So I really do have 1 over u du, or equivalently u prime over u. So my choice for u in this case would be the tangent of x, because that way when I take its derivative with respect to x, I get secant squared x, which is really 1 over cosine squared x dx. I've got my little dx on there. So when I write this, I actually do have 1 over u du, which is ln absolute value of u plus Carl. And I'm done. So I think I have 2 more on the next page, and that'll be it for this section of notes. So my gut instinct is to take the 4 out front. Keep in mind now I'm doing a definite integral. I've got limits of integration, so my answer will be a number. I will be using the fundamental theorem of calculus, but first I'm going to pull out the 4 just because I like to, not because I have to. Whenever I see a fraction, I immediately go to the bottom, and I hope that its derivative is on the top, or a multiple of it is on the top. So when I let u equal 2x plus 1, I end up getting my du as 2 dx, and I end up getting 1/2 du is 1 dx. So I really can write that whole integral as, I purposely left the limits off because here's why. If I am going to write this as 1 over u du, and that was actually a 1/2 du, then my limits can't be my limits for x, which was 0 to 4, right? I can't use x limits on a u problem. So remember how we counter that? We do a limit change. When I put in a 0 for x, u is a 1. And when I put in a 4 for x, u is a 9. So really what I get here is 2. And then the antiderivative of 1 over u du is the natural log of the absolute value of u. And I am going to be evaluating that from 1 up to 9. Remember, to do that, we do top function, or top limit minus the function evaluated at the bottom limit. I don't need the absolute values on positive numbers. Natural log of 1 is 0. So I end up getting 2 ln 9. Now the sad thing would be is if you went through all this work and it was multiple choice and you looked at A, B, C, D, E, and you didn't see 2 ln 9 sitting there, so you think you did it wrong. So you need to have the ability to play with logarithms. And what that means is if they don't have 2 ln 9, maybe when you bring the power in, that's sitting there. Or maybe if you wrote this as 3 squared or this as 3 to the 4th, watch what happens. When you bring the power up front, you get 4 ln 3. And maybe that's what was sitting here and you just didn't recognize it. So you'd hate to go through all that work and then not be able to play with logarithms well enough to find your right answer. So any of these are legal answers for that problem. Off to the next one, and this will be the last one in this section, and the assignment is worksheet 5.2a, numbers 1 through 15, and there's a key attached to that as well. So my gut instinct is to let u equal the natural log of x, because I can see that its derivative is the entire rest of the integrand. However, I'm going to do a limit change here because my limits are for x. So when I do ln e, natural log of e is 1. When I do ln e squared, the ln cancels out the e, or you can think of it as 2 ln e, but I get a 2. So when I reset up my integral, what I'm going to be evaluating is from 1 to 2. I've got u on the bottom as ln x. The rest of that is du. And I get natural log of u, absolute value, evaluated, my limits for u are 1 to 2, which would give me ln 2 minus ln 1. Natural log of 1 is 0 because e to the 0 is 1, and I get the natural log of 2. Now let's discuss if you didn't do the limit change. I'm going to go over here. If you did not do the limit change and you back substituted, then you would have ln of ln x evaluated from e to e squared. And so see, what you would do is you would plug this in first and you go ln e squared is 2. So you'd get ln 2 minus ln e is 1, and you get ln 1. You'd notice that that goes to 0, and it all wash out. I think the limit change is more eloquent. I think the limit change lends itself to better notation. So I think you should get used to changing your limits right here when you do definite integrals with u substitution. That's it for 5.2a. The assignment is the worksheet 1 through 15. It is in Edmodo, and so is its key.